Let's take a look at implementing queue using stacks from Grind75. Implement a first in, first out FIFO queue using only 2 stacks. The implemented queue should support all the functions of a normal queue: push, peek, pop, and empty. Implement the myQueue class. It's got to have 4 different functionalities. It's got to have a function called push, pushes integers; pop, that'll remove the element from the front of the queue; peek, which will just return the element at the front of the queue without removing it from the collection; and empty, that'll return true if the queue is empty, false otherwise. Notes: you must use only standard operations of a stack, which means only use push to top, peek from top, size, and isEmpty operations are valid. Depending on your language, the stack may not be supported natively. You may simulate a stack using a list or deck, double-ended queue, as long as you only use a stack's standard operations. So the first example, this is basically your standard queue, right? Whatever you push first is going to be the first thing that you are going to get out of the queue, right? So if you push 1, 2, 3, 4, 5, for example, whenever you do a peek or pop, you're going to get the 1 and not the 5. And that's basically all this is saying. Constraints are such that X is going to be between 1 and 9. At most, 100 calls will be made to push, pop, peek, and empty. All the calls to pop and peek are valid. Follow-up: can you implement the queue such that each operation is amortized in constant time complexity? In other words, performing n operations will take overall O of n time, even if one of those operations may take longer. And that is kind of a hint. All right, so let's jump into the code, or not the code. Let's jump into a diagram to see how we could solve this. Implement queue using stacks, and we're basically from the get-go going to go straight for the optimized solution that they're talking about. The amortized constant time basically is typically a hint that you're going to, in some cases, perform an operation that might be O of n, but overall, most of the operations are going to be in constant time. So let's take a look at an example using 2 arrays. So whenever we want to push a value, we're always going to push it to the first array, right? So if I push a 1 here, this is going to be in our array, right? And then if we push a 2, then we push a 3, and then we push a 4, these are all going to go to the first array. So every single time, no matter what, we're always going to be pushing to the first. That's the first bit. But whenever we want to grab this value down here from the bottom of the array, you may remember that in Swift, and as well as many other languages, whenever you want to remove this element, you basically got to shift all the elements down, which can take O of n times, which is something you want to avoid. So if you were to do this every single time, that's not going to give you that amortized constant time. So the way around this is whenever we want to peek or pop, what we're going to do is basically copy over all of the elements from the first array to the second array in reverse order. So instead of 4, 3, 2, 1, right, we're going to have 4, 3, 2, 1. And then we're going to remove all the elements from the first array, so the array will be empty at this point. And then we're basically going to grab or peek from the element at the very top. And the isEmpty basically is a simple implementation. You're basically seeing, is the first array empty and is the second array empty? Although I said that backwards. And if they're both empty, then obviously the whole thing is empty. But if one of them has values, then obviously your queue is not empty. So this is going to take, all the operations are going to take an amortized constant time. And the reason why we say amortized is because every once in a while, let's say we pushed a lot of values to our first array. Whenever we want to perform a peek or a pop, we're actually going to have to copy over all the elements, which will take O of n time. It's just that this is the more often that we do this operation, the less likely it is to occur. So once we've copied over many values, for example, whenever we do a peek or pop, we've already got values in our second array, so we're not going to need to do that. And space complexity will be O of n. Even if it is 2n, that will be reduced to O of n. All right, let's take a look at the code now. The first thing I want to do in my queue is basically set up those arrays I mentioned, right? So we're going to have the first array, and that's going to be an array of integers, and the second array is going to be the same thing. It's going to be an array of integers. Great. I'm just going to collapse this constructor here because we're not going to be using it. So every time we push, we need to access our first array and append the element. That is the complete implementation of the push. The pop and the peek, however, are going to need a little bit of help because they're going to need to copy the elements from the first array to the second. I'm going to make a private function here called copy elements from first to second. And this is going to say, all right, if the second array dot, I'm going to say guard second array dot is empty, else return, meaning we don't actually need to do anything because our array is not empty at that point. We're going to say second array is equal to first array dot reversed, first array dot remove all. So we're going to copy over all the elements from the first array, and we're going to remove everything from the first array. And we're going to call this function from both the pop and the peek. And then we're going to say, so for the pop, we actually will be modifying the array. So we're going to say return second array dot remove last. Remove last will actually crash in the case where there's no elements. However, the problem is written in such a way that invalid operations will never happen. So we don't got to worry about that. The peek is very similar. However, we're not going to be modifying the second array. Rather, we're going to be returning the second array's last element. And that should be almost the whole code. We just need to populate this empty function. The empty function is going to be pretty simple. We're going to say first array dot is empty and second array dot is empty. Basically, you need two empty arrays to be considered empty. So if I run this code, it should be good. And if I submit it again, there you go. I hope you've enjoyed this video.